Hello, welcome to the lecture of engineering mechanics. In this video, we will discuss dynamics. Okay, specifically, we'll focus on rectilinear motion. So, actually, if you divide dynamics, this dynamics can be classified into two parts. The first one will be called as kinematics. The other one will be called as kinetics. So what is different? See, dynamics is nothing but the motion study. We will be studying the motion, dynamic condition, the motion study. Whenever any object is in motion, we will analyze some parameter related to the motion. So in the kinematics, we will study the motion without considering the force. But here in the kinetics part, we will consider the force, then we will analyze the motion. Okay, here force will be considered. In the kinematics, force will not be considered. This is the classification of dynamics. Okay. So again, this part, in this part, we will be only discussing the terms which are not acquainted with the force, and in the kinetics part we will discuss the terms which are related to force. So we'll start with rectilinear motion. In the dynamics, we have to cover, see, in the syllabus of diploma, the dynamics only we have rectilinear motion and collision. Two things are there in the syllabus, actual syllabus. But in the previous year of the ATU mains examination, there is a concept from general plane motion, circular plane motion. Actually, in the last year, some of the gate question were included in the paper. Okay, so we'll cover like rectilinear motion. Then we'll talk about the motion along the curve, that is curvilinear motion. Whenever any object is moving in a curved path, okay, that is curvilinear motion. Then we'll talk about rotation of any rigid body. Okay, how an object will rotate, like a ceiling fan is rotating. Okay, then in the last we'll talk about the impact, that is if you just wait. In the fourth part we will talk about principles. Okay, the principles, if possible, in this video what I will do, some principle, there are 2 to 3 principle, I will include the momentum principle over here. If time possible, I will cover collision in this video only. Okay, so in the collision part will be covered in the rectilinear motion. Then there will be maximum to maximum 3 video. In the 3 video we can cover dynamics in short duration of time. Okay, now we'll go for rectilinear motion. So what is rectilinear motion? Can you explain? See, whatever rectilinear motion is nothing but, in simple, if I will tell you, rectilinear motion is nothing but straight line motion, motion along a straight path. You have a straight path over which the object is moving, that's called straight line motion or rectilinear motion. This one is very simple. What is dynamics? See, dynamics, if in a single word I want to describe what is dynamics, the whole thing can be just understanding. It is nothing but understanding Newton's second law. Okay, net force is equal to mass into acceleration. If you can understand this Newton's second law in different situation, then dynamics will be okay. See, you have to focus on the concept in this chapter, else you cannot attempt any question from the dynamics, because this one is a very conceptual chapter. Okay, whatever we have discussed in up to this point of time, that was the statics part. Here is the main, you have to apply some conceptual thing. Okay, then only you will be able to solve question related to dynamics. So before starting rectilinear motion, I want to write some of the terms which will be used in this motion. Okay, so the first term I'm writing over here, you should know inertia force. Inertia force, I'm writing from starting from inertia. Okay, what is inertia force? Because we are dealing with dynamic, the body is not at rest. So inertia force means, in the first chapter I have discussed with you guys that force having three characteristics. The first one is magnitude, second one is direction, third one is the point of application. If you change any one of the three, then the effect due to that force will change. So inertia force having three characteristics. Number one, the magnitude. Okay, the second one, direction. The third one, point of application, where the force of inertia will be applied. So what is the magnitude? Magnitude is simple, nothing but mass into acceleration. Okay, direction is, I'm writing, it's opposite to acceleration. The point of application is nothing but at the center of gravity of the object. Okay, I'm writing three characteristics you have to remember as far as inertia force is concerned. So suppose I'm taking an object like this. See, this is an object. What I'm saying, this object is in the plane, okay, in a straight horizontal plane. So this is a plane over which this object is placed. The object, I'm saying, the object is not at rest, it's in dynamic condition, it is having some velocity. Okay, why it is moving? Because some force is applied on this object. Okay, so I don't know the position in between. Now I'm saying, we have studied the equilibrium concept, net force in horizontal direction is equal to 0. That concept will be applicable only when the body is at rest. If you want to apply that condition of equilibrium in a dynamic body, you have to apply an extra force called inertia force. Okay, this body is in moving with this force, then what you need to do, you need to apply an force. Where you have to apply? You have to apply at the center of gravity of the object. Okay, this one having a magnitude of ma. If the object is accelerating in this direction, you have to apply the inertia force in the opposite direction to the acceleration. Opposite direction to the opposite to the acceleration. These are the three things you have to remember. So this is nothing but D'Alembert principle. Okay, so in a dynamic equilibrium, whenever you want to apply the equilibrium concept to a dynamic body, you have to apply this inertia force. Dynamic equilibrium. So this one, with the concept of this one, I will not take anything because we have thoroughly revised the equilibrium part. Okay, net force in x direction is equal to 0, net force in y direction is equal to 0, net moment about any point is 0. These are the things we have discussed thoroughly. So we will extend this concept to dynamics, then we can solve any question irrespective of the situation given. Okay, so this one is the inertia force. You should have the clarity what is inertia force. If you will ask me some example related to inertia force, see, suppose this is the road, okay, over which there is a boss. Okay, in this bus there are several people are sitting over here. Okay, like this there are many people. What is happening, if you consider any one person, okay, I'm just considering any single person, so I'm saying there is a single person over here. So this person having a mass, suppose see the boss is accelerating in this direction, it is in dynamic condition. Okay, so the object having a mass in downward direction, the weight, that doesn't matter. See the force, since the force, the object is accelerating, why it is accelerating? Because of the friction only, because the boss is moving in the forward direction. Why the man is also moving in forward direction? Because he is sitting over the boss, because of the friction. Okay, if he is standing, suppose you consider he is standing, why the boss is moving, why he is moving? Because of the frictional force. Frictional force is trying to move this person in the forward direction also. So this object is not in the static condition. So if you want to apply the equilibrium condition, you just need to, at the center of gravity of the man, you just applied an dynamic inertia force that's called mass into acceleration opposite to the acceleration direction. So why? See, this inertia force, I'm saying, for the equilibrium in the dynamic condition, the boss is moving. What I'm saying, boss is moving. Boss is moving. On the boss, this person is standing over there. Is the man is moving? No, the man is at resting. In the dynamic condition also, the man is in the static dynamic equilibrium condition. How? Because there is a balanced inertia force is applied. Okay, the friction direction is over here in the forward direction. Due to the inertia force, the man is standing. Okay, whenever the boss will stop, whenever the acceleration will be reduced, what will happen? The inertia force value will decrease. So the inertia is in the downward, in the backward direction of the person. So whenever the driver will apply the force, what will happen? The inertia force value, as acceleration decreases, the inertia force will also decrease. So inertia in the backward direction, what will happen? The forward force will be more. So the person will just go 1 to 2 steps in the forward direction. Okay, this is the condition whenever the brake is being applied by the driver. If you talk about another case where the boss is at the static condition, the acceleration is increasing. So since the acceleration into multiplication of the acceleration with the mass is nothing but inertia force in the opposite direction to the acceleration, as the acceleration will increase, what will happen? The inertia force will also increase. So what will happen? Whenever a boss is at the static condition, the driver is accelerating from zero velocity to and some final velocity. What is happening? The acceleration is increasing. In that condition, the inertia force is increasing. So whenever the boss is accelerating, you will experience a backward force, that is the, so that you will go 1 to 2 step back. Okay, that's what inertia force is all about. Okay, so with this inertia force concept, we can do any problem which will be given in the examination related to rectilinear motion. Okay, now we should discuss Newton's law. Okay, Newton's law, what I'm saying, the first law is nothing but inertia. Okay, law of inertia. The statement is simple. What it is saying, if any object is at rest, that object will try to be in that state only. If the object is in the rest, the velocity is equal to 0. In that case, the object will try to be in that rest position only. If the object is in uniform motion, okay, if the object is in moving with some velocity v, then the object will also try to be in that uniform motion. Okay, that is called law of inertia. We have discussed in the last video what is inertia. Okay, Inertia is nothing but it's the resistance to the changes. Since the object is at the rest, the object will try to be at the rest. If the object is in motion, the object will try to be in the motion itself. The second law is the one which will play an important role. The statement of Newton's second law is saying the rate of change of, I'll see, listen the statement, the rate of change of momentum. Okay, the rate of change of momentum is nothing but the external force applied. So I'm saying momentum, you know what, mass into velocity. Mass into velocity is nothing but momentum. Okay, rate means the rate of change of with respect to time, the change of this momentum. Is saying, suppose this momentum will be represented with p. Okay, I'm saying the second law is saying the rate of change of momentum with respect to time. Okay, the rate of change of momentum is nothing but external force, net force. So this is the statement from the Newton's second law. What we can do, see, if I'm writing net force is equal to d by dt of mass into velocity. Okay, velocity, it's a vector quantity. You have to always, in the dynamics, you have to always give importance to the direction. If you give importance to the direction, then only the answer will be correct. Else you will be putting the same value, exact value, but the direction is changed, so the answer will be wrong. Okay. So net force, I can write d by dt of mass into velocity. Mass is constant for any object. I'm taking out of the derivative, so it will be derivative of velocity vector with respect to time. So this one is nothing but how much? This one is nothing but acceleration. So the formula is coming out to us mass into acceleration. So in general, we are saying net force is equal to mass into acceleration. Okay, this is the formula we are being using. Okay, we have been using from our childhood. But the actual statement is saying the rate of change of momentum will give you the external force. Whatever force you are applying on an object, that force you can calculate, whose value will be mass into acceleration. Okay, the third law is saying the action reaction. The action and reaction. That means he's saying, suppose you have an wall over here. Okay, this is a wall. You are applying an force of P Newton. So the wall will give you another reaction. The wall will give you another reaction to your application. So that will be reaction. So whenever you will apply an action, you will get a reaction. Suppose, see, there is a, this one, suppose I'm saying this one is a, okay, suppose this one is a gun. Okay, this one is a gun. What will happen? There is a bullet which will be going out from the barrel of the gun. So you will get a reaction. The force will be in this direction, so that the gun is moving in the forward direction, the bullet is moving in the forward direction, but you will experience a backward force. Okay, so that's called reaction force. So this is the action force by the gun, and the bullet will give you an reaction force. So you, whenever you will fire an gun, you will experience a backward force. Okay, that's all about action reaction. Okay, so you just need to remember net force is equal to mass into acceleration. Okay, what is this velocity, momentum, we will discuss in detail. Now I'm starting all the terms which will be used in the terms. Okay, I'll be writing the terms. You should know the fundamentals. Okay, so the first term I want to discuss with you guys is nothing but displacement. This displacement is a vector. Okay, it's a vector quantity. It is having and magnitude as well as direction. It is represented as s vector. Okay, so the distance means the length between 2 points is known as distance. Suppose I'm taking 2 points. See, here is the 2 point, number 1, number 2. Suppose this point having an coordinate like x1, y1, here having an point x2, y2. Okay, so if you want to calculate the displacement, okay, that will be the shortest distance between the point A and B. You can travel in any path like this. See, you can go like this, you can go like this, you can go like this. Okay, so the final, these are called distance. The shortest distance between the 2 points is called displacement. So the distance is a scalar quantity, but the displacement is a vector quantity. It is having a direction. Okay, you have to go this amount of distance in this direction, that's called displacement. Okay, so displacement, if I'll write in the formula, so I can write s vector from A to B. I'll write over here s ab, that's a vector quantity. I can write x2 minus x1, that this amount of distance I have to go in I direction, that is in the x cap, plus you have to go in upward direction, so I'll be writing y2 minus y1 j cap. This one will be the vector, that is the shortest distance. I'm writing in the vector form. Okay, so this one all about displacement having an unit of meter. You should always, whenever I'm writing any vector, okay, vector means you have to look at the direction. Okay, if you are missing the direction, then the answer will be come out to be wrong. Okay, so the displacement can be positive or the displacement can be negative depending upon the direction in case of rectilinear motion, because in the rectilinear motion the object will be in a straight line, so there will be in a forward direction, backward direction. These two are parallel to each other. Okay, so we will do the next term, the second term, that's called velocity. Velocity vector is represented as v vector. Okay, what is velocity? He's simple saying the velocity vector is nothing but the rate of change of the displacement. The rate of change of displacement with respect to time is called velocity vector. Okay, everything I'm writing in case in the term of vector. Okay, if you want to remove this vector, you have to consider in a particular direction. Vector means you are up, you are dealing with direction. Okay, you are dealing with direction. So if you want to apply this equation, you have to apply in a particular direction. In that case you can write, I'll write in a particular direction, the velocity will be equal to ds by dt. That as simple as this. Okay, so see, the velocity is the rate of change of displacement is known as velocity. There is something called speed. Speed, what is speed? Speed is nothing but the magnitude of the velocity vector. That means he's saying the distance by time. Distance is a magnitude having no direction. The distance by time is known as speed. So it is nothing but the magnitude of the velocity vector is the speed between these 2 points. If you are having an change, suppose, see, the example will be like this. You have 2 points. Okay, this is a point number A and this is the point number B. You are traveling a distance of s. If I'll tell you what is the displacement, that is s. In how much time you are covering this displacement? In the time interval of t second. Okay, in the s meter, in the time interval of t second, you are traveling from point A to point B. In that situation you will write the velocity is nothing but a distance, the displacement by time. That's the velocity. If you are saying in a particular direction, that will be the velocity. Okay, here is a distance. Okay, suppose this is the distance, so the speed will be nothing but distance by the time taken. Okay, so you got the idea about displacement and velocity. Now the third term is the acceleration. Okay, so in the velocity, it's a vector quantity. So I can write the velocity in the component form, that is Vx I cap plus Vy j cap, okay, plus Vz k cap. Like in the first chapter, we know how to represent a vector. If you want to calculate the magnitude of the vector, it will be nothing but Vx square plus Vy square. Okay, these are the way to calculate the velocity. If different direction component, that is the velocity in the direction of x, this is the velocity magnitude in the direction of y, in that case you can calculate the magnitude of the velocity. So the Vx will be nothing but how much? The Vx will be the dx, the distance by in the displacement in x direction divided by dt. Then Vy will be nothing but dy by dt. Okay, these are the term you can easily calculate. There is something called average velocity. Average velocity. Average velocity means total displacement divided by the total time. That's called average velocity. Okay. Similarly, average speed means total distance by total time. The instantaneous velocity means at a particular instant of time, what is the velocity? That means dv by dt. Okay, we can write, sorry, ds by dt, that is nothing but the instantaneous velocity. Now we'll go for the next term, that's called acceleration. Okay, so the third term is nothing but acceleration. So what is acceleration? Acceleration is nothing but the rate of change of velocity. Okay, the rate of change of velocity is known as acceleration. Getting my point? Acceleration is also a vector quantity. Okay, acceleration is nothing but the rate of change of velocity with respect to time. If you talk about in x direction, okay, I'm talking about in x direction, what will be the acceleration? Ax will be writing as dvx divided by dt. So the vx means the velocity. Velocity, you know what? D by dt of, if I'll write the dx vx, that is nothing but dx by dt. So I can write d square x by dt, sorry, dt square, that is the second derivative of the displacement, is known as acceleration. So it's a second derivative. Okay, second derivative. Can you tell me what is derivative? Derivative is nothing but derivative, whatever I'm writing over here, this is nothing but the changes. Okay, the change in something, the change, that means the final minus initial, that what I'm writing. Okay, I'm saying dv means the final velocity minus initial velocity. Okay, with respect to time, I'll divide with the time. That's what I'm saying, in a particular direction. So this one is the rate of change of velocity, is known as acceleration. If you want to apply in a particular direction, you can remove the vector, then you can apply easily. So there are other terms like average acceleration. Average acceleration. What is average acceleration? The total change in velocity divided by the total time taken, that will be the average acceleration. Okay, the instantaneous acceleration is nothing but the rate of change of velocity with respect to time at a particular instant, that is this one is the instantaneous acceleration. Here what I'm saying, suppose you are traveling from one point to this point, this distance, suppose 100 kilometer. Okay, this one is like 100 kilometer. What I'm saying, listen carefully. If you are traveling by a car and 100 kilometer, are you going to maintain your speed over the whole distance as constant? No, not at all. There will be humps, there will be tools, all the things will come out. So the velocity is varying. That means the acceleration is not constant throughout. So there will be two situations. The acceleration, there will be the acceleration, I can write, there will be some will be uniform, the other one will be non-uniform. The uniform means the acceleration is constant throughout. That means the velocity is constant whatever distance you are covering. In that total distance, the acceleration is constant. That means the velocity is constant, acceleration is uniform. Okay. In the non-uniform, acceleration is not constant. There is a increase decrease in acceleration value. Okay, that's called non-uniform. So for the uniform motion means acceleration is constant. We have some equation of motion. In uniform acceleration, we have equation of motion. That equation of motion, this one can be derived, equation of motion, from the definition, simple definition, whatever we have discussed, displacement, velocity and acceleration. With the help of these three definition, we can write the equation of motion by treating acceleration is equal to constant. Okay. So I'm repeatedly saying you should always concentrate on the direction. So why the acceleration is constant? See, acceleration is being produced by the force. Since here, over here, I will write the net force you are applying, that's constant. That's why you are getting an acceleration which will be constant. If the net force is varying, is not constant, then only you are getting a variable acceleration. Getting my point? So in the uniform motion, the net force is constant. We'll write the equation of motion. So in the next one, I'm writing equation of motion. See, there are four equations. You have to remember, okay, and you can directly derive on the spot also. The number one, that is nothing but v, the final velocity is equal to u plus at. Okay, these are the vectors. Okay, you have to consider the direction. I'm taking in a particular direction, so I'm removing the vectors. Number two will be like v square, final velocity square will be equal to v square is equal to u square plus 2as. The third one is nothing but the displacement, s is equal to ut plus half at square. If the fourth one you want to write, that one will be like s, the distance by time, you know, the velocity average, so I can write time into v average. Okay, so v average, that is nothing but t by 2 into, sorry, this one is average, so I'll write t into v average is nothing but initial plus final divided by 2 that is the average. Okay, u plus v divided by 2. These are the four equations you can apply in a particular direction. You should remember, in a particular direction, whenever the acceleration is constant. This one is most important. The acceleration must be constant. Then only you can apply these four equations. If anyone want to prove this equation, you can easily prove over here. Okay, see how you are proving. The acceleration is nothing but dv by dt. Okay, in a particular direction I can write dv minus u by dt. So I'm writing a dt is equal to dv minus du. If I'll integrate over here, I'll get at is equal to v minus u. So v is equal to u plus at. Similar way you can prove by the definition, you can prove all these four equations, okay, on the spot. We have discussed acceleration is nothing but d square x divided by dt square. If I'm taking displacement as s, d square s divided by dt square. From here you can prove, okay, else you can write acceleration, we have discussed dv by dt. If I'll use the chain rule, what I'm writing, I'm multiplying in the denominator by ds, in the denominator by ds. So the du by ds, okay, this one. So I'm writing du by ds. the ds by dt is nothing but velocity. So acceleration, I can write the velocity into du by ds with respect to displacement. In this form also you can write the acceleration. Okay, so this was the equation of motion. Okay, in a particular direction you have to apply, you just remember this much. Okay, now up to this point of time we have discussed four terms: the inertia, force, then displacement, velocity, acceleration. Now we'll go for the other terms as well, the fourth, fifth term. Okay, how many terms? Three terms. Inertia force is different thing. Okay, you have to take care of inertia force having three things: magnitude, direction, point of application. So I'm writing linear momentum. So it's linear momentum. What is linear momentum? Momentum, is mass into velocity. Some momentum, this momentum is the cause behind inertia. That means it will try to maintain a flow. If you are saying na, the examination, in the flow of examination, I have got some momentum, so the study was good. Once the momentum will be lost or break, the effectiveness of study will decrease. So that's what momentum is all about. Sorry, I'm writing moment over here. It's momentum. Moment means the force into perpendicular distance. Here is the momentum. Okay, it is nothing but a p vector. Okay, it is represented as p vector. Linear momentum is nothing but mass into velocity vector. Okay, this is the definition. Mass into velocity is known as momentum. The rate of change of momentum is known as external force by the Newton's second law. We have already discussed. If I will write over here, the net external force is nothing but rate of change of momentum with respect to time. So dp by dt in a particular direction, I'm saying. So I can write net force. See, whenever I'm not writing the vector, that means I'm talking about in a particular direction. You should remember always. F dt will be equal to how much? dp. If I'll integrate this one, so this one, you will get how much? The del p, that is nothing but mv minus mu. Okay, the final momentum minus initial momentum is the change in momentum. So the change in momentum you are getting as integration of f dt. This one from the Newton's second law, we are deriving from Newton's second law. So this one called impulse, force into time, the momentum, change in momentum. Okay, this one is called change in momentum. So impulse is nothing but change in momentum. This is in principle. I can write over here net force into dt. Okay, net external force with respect to time is nothing but mv minus mu. This one is a principle that's called impulse momentum principle. Impulse momentum principle. Whatever I was saying now in the initial discussion of dynamics, I was talking about there are four principles we have discussed. So out of the four, I have discussed the number one, which is nothing but Newton's second law in a different form. So in this, you have to only remember one thing, that the whatever force you are applying, it's external force, not inertia force. It's external force. Okay, the Newton's second law, the force is not a inertia force. You don't need to consider inertia force, only external force. Okay, you should remember. The impulse momentum principle is saying simply the impulse, the linear impulse is equal to change in momentum. Okay, so we are writing another term, that is nothing but linear impulse. The value of linear impulse is f dt. the force into time. Okay, so net external force into time is equal to linear impulse. It is also a vector quantity. Okay, you have to apply in a particular direction. So up to these, the 5 term, the displacement, velocity, acceleration, linear momentum and impulse, these 5 are vectors. Okay, so you have to take care of the direction. And in the calculation of impulse, the net force is not inertia force. I'm talking about external force. There are another 5 more terms have to be discussed. So this one is the 5th term. Let's go into the 6th one. The 6th, that is nothing but the work done. So what is work done? Work done, simply, if I'll write the definition of work done, the work done is nothing but the dot product of force vector into the displacement vector, Fs. Okay, I can write Fs cos theta. Dot product is nothing but Fs cos theta. Okay, so if theta is equal to 0 degree, the cos theta will be 1. If theta is equal to 90 degree, what will happen? The cos theta will be 0. If theta is equal to 180 degree, the cos theta will be -1. We know this thing. So if you are taking in a particular direction, suppose the force vector and displacement vector, this is the force vector, this is the displacement vector, having theta is equal to 0 degree, in this case the work done will be nothing but the force into the distance, that is the force into distance is the work done. Okay, if they are in opposite direction, what will happen? The work done will be equal to minus Fs, F into S. Okay, not the cross product, I'm just writing the normal algebraic multiplication. If they are perpendicular to each other, suppose the force in the x direction and the displacement in the y direction. Okay, so in this situation, the work done is equal to 0. Okay, whenever the force vector and displacement are perpendicular to each other. So this one is the force into distance, the dot product of force into displacement is nothing but work done. It is a scalar quantity. Okay, the dot product will result a scalar result. Okay, so this is a scalar. You no need to scalar quantity. You no need to take care of the direction over here. But if I'll discuss Newton's second law over here, I will get another principle. See what I'm saying. The net external force is nothing but the rate of change of momentum, that is mv vector divided by dt. I can write in this way. So if I'm taking the mass out of the derivative, it's dv vector by dt vector. So this one is nothing but I can write, see, in this way, dv vector, I'll write over here like this, mass into acceleration. This is the Newton's second law. From here, if I want to, I will remove the, which one? The vector. Okay, I'm just writing in normal, in a particular direction, in a particular direction. If I'll apply, so net external force will be nothing but how much? M will be taken out of the, so I'm writing dv by dt, this one, dv by dt. So what I'm saying, mass into dv by dt, in the numerator ds, in the denominator I'm multiplying ds. So I can write mass into ds by dt, this portion. Okay, ds by dt is nothing but velocity into dv by ds will be left out. So you are getting how much? You are getting net external force is equal to mass into velocity into dv by ds. Okay, this is nothing but Newton's second law in other form. So from here I can write, so see, I'm writing from here net force into the displacement, that is nothing but work done, is equal to mv dv. If I'll take integrate in both the side, I'll get like this: net force into the displacement derivative will be, the s will be equal to mass velocity into dv, that will be v square by 2 from the point u initial to final v. So from u to v I'll write m by 2 v square minus u square, simple derivative. So that this one is net force into displacement. So you are getting how much? You are getting net external force. Okay, net external force into displacement in a particular direction is equal to half m v square minus half m u square. So this one is also in principle. Okay, this one is a principle. Okay, so what I'm saying, the work done, the force into displacement, work done is equal to change in kinetic energy. So this one is a principle. How we derive? From the Newton's second law itself. So it is nothing but another form of Newton's second law. Okay, so the net work done is equal to change in kinetic energy. In the first principle, net impulse, linear impulse, is equal to change in momentum. Okay, so the second one we got work done is equal to change in kinetic energy. Okay, so this one was work done. Next term I will talk about the seventh one, potential energy. The value of potential energy is nothing but mg, that is weight into height, mgh. Okay, this one. So this is the energy responsible for positioning. Okay, energy because of positioning. Energy because of positioning. Suppose I'm taking this one is the reference line. Okay, over here there is an object. So the potential energy, if there is a structure like this, the ball is resting at this, I'm taking this one is the reference axis. So the potential energy will be mg into height. If the block is at a above distance, mg h2, this one will having an mg h1, this one having potential mg h2. It's depending upon the height from the reference axis. Okay, so this is nothing but it's also a scalar. So it is simple, potential energy is mgh. You just need to remember the formula. And the reference axis we are taking by our choice, or it will be given in the question. Okay, with respect to the reference we are calculating potential energy. If you change the reference or datum, the potential energy magnitude will change. It don't have any direction. Okay, so the eighth one I'll be writing the next term, that's called kinetic energy. Kinetic energy is simple, nothing but half mv square. Okay, half mv square is the formula of kinetic energy. It is because of the energy because of motion, energy because of whenever any object in motion, that object will have some kinetic energy. Okay, the ninth term will be the spring energy. If you are having a spring like this, okay, and you are applying a force over here, so this one is F, so you can write F is equal to how much? K into X. This is the force. K is the spring constant of the, and X is the deflection, whatever deflection you will get in the spring. But the energy, spring energy, okay, energy, spring energy is equal to half K X square. Similar to the equation of half mv square, it is called half K X square. Okay, X is nothing but the deflection in the spring. So whenever the spring will be deflected, you are changing the length of the spring, there is a storage of energy in the form of spring energy. Okay, so this is spring energy. The last one, the 10th term, is nothing but total energy. Total energy of any object is nothing but the sum of the kinetic energy, so sum of the kinetic energy plus potential energy plus spring energy. Okay, these are the 10 terms we have to use in rectilinear motion. So the first 5 were vector quantity, you have to take care of direction, and the rest 5 are scalar quantity, and you can find unit of each whatever term I have discussed. You can find unit and dimension as well for MCQ. Okay, and this concept will be used in numericals. And one more thing, if you will apply, if you want to discuss, that's called relative velocity, which will be used in question. Relative velocity is nothing but, suppose this one is a block, here is a block, this one is moving at a velocity of 5, this one is moving at a velocity of 3. So this one A, this one body is B. So velocity of A with respect to B will be nothing but VA minus BB. So you can write 5 minus 3 is equal to 2 is the relative velocity of the A with respect to B. If you are sitting at a point B and you are observing what is the velocity of A, that's called velocity of A with respect to B. With respect to B means at the position B, you are sitting at the position B and observing the object A. That's the relative velocity. Okay, VA minus BB. So if you want velocity of B with respect to A, that means you are standing over here and you are observing the velocity of B. That is velocity of B minus velocity of A. So these are very simple concept with respect to relative velocity. So up to this, all the term we have discussed related to rectilinear motion. Now I am giving you the principle, whatever principle we have got. See, there are 3 principles we have to discuss. The number 1, impulse, that means net force, external force into time, that is linear impulse. Integration is nothing but change in momentum, mv minus me. This one is the first principle. So I am talking about principle. The second one, net force into displacement is nothing but half mv square minus half mu square. So the work done is nothing but change in kinetic energy. The third principle is saying energy conservation. What it is saying? Energy can neither be created, nor be destroyed. You can't make any energy, okay? You can't destroy any energy, nor be destroyed. Only energy transform from one form to another. That means he's saying you can change kinetic energy into potential energy into kinetic energy. You can change any energy, but you cannot create or destroy energy. Okay, this is the energy conservation you have to apply between 2 points. between any two point. Okay, so these are the three principle. With the help of this, any question can be solved. So this one is the linear impulse. This principle called impulse momentum principle. Impulse momentum. This one is called work done, change in kinetic energy. Okay, sorry, kinetic energy. Okay, so these are the external force, not inertia force. Okay, we'll do some numerical, clarity will be there. So I'm summarizing whatever we have discussed up to this. The summary of this video. First we talk about inertia force, having a magnitude mass into acceleration, opposite to acceleration. It will be applied at the center of gravity. Okay, point of application. Then we discuss displacement. Then we talk about velocity vector is nothing but rate of change of displacement vector. Then we talk about acceleration, that is nothing but dv vector by dt vector. If you are applying in a particular direction, ax will be equal to dvx by dt. Okay, then if it is in a uniform, acceleration is constant. Acceleration is not constant, non-uniform. For acceleration is equal to constant, we have discussed 4 equation. V is equal to u plus at. In a particular direction you have to apply. B square is equal to u square plus 2as. Then the third one, s is equal to ut plus half at square. The fourth one is nothing but the displacement is equal to time into v average, that is t by 2 v plus u. Okay, these are the 4 equation. Then we discussed about linear momentum, that is nothing but mass into velocity vector. Then impulse is nothing but force into time. Then we talk about work done, the dot product of force into s vector, it's a scalar. Then we talk about potential energy, mgh. Then we talk about kinetic energy, half mv square. Then spring energy, half kx square. Then in the final, total energy is the sum of potential energy plus kinetic energy plus spring energy. Then we talk about the principles. The principles are like this: net impulse, that is F net external force into time, is nothing but change in momentum mv. Okay, change in momentum. Then the second one is like this: work done F into ds is equal to change in kinetic energy. The third one is energy conservation. I'll give you some of the application of these, all the equation whatever we have discussed in this video. We'll do some numerical. Okay, so these are the concepts we have discussed in this video. Thank you for watching. In the next video we'll discuss all the remaining concept, then we'll do some numerical. Thank you. We'll see you in the next video.